Okay, so what I thought I would do to begin with is just describe how you're determining your grade in this course. So this is the logic that will be used for your interim grade and then ultimately your final grade. And then we'll get back to the IR. So you have required course points. So under the required, your total quiz sum for Module 1 was 48 points. Module 1 exam was 60. So far for Module 2, you have 24 quiz points. And then your Module 2A exam opens today. That's worth 60. So that's 192. That's the required points. And so that goes in the denominator here when you're calculating percent. So bonus points, if you subscribe to YouTube, that's 6. So that's sort of all or nothing. The practice exam was out of 30 points. So whatever you got out of that. And then this DF is discriminant factor. And so again, that is something that's spit out from ZipGrade based on the quizzes only. So everyone will get 12.5 points. So whatever you got, number of points, your required plus your bonus divided by 192. And then the grading scale, 80 or above is an A, 60, a B, 40, C, 20, D, and then 0 is F. So please note, Excel is like the Terminator. It does not have feelings, so it does not round. So I'm not putting a rounding function in Excel. If you're at 79.8, that is not going to be rounded to 80. Keep in mind, Canvas is not a spreadsheet. So you basically sort of need to do this stuff on your own. Canvas does not allow me or any other instructor to go in and add functions to columns, to do adding, subtracting, that sort of thing. So all you're going to do is just take your points, add them together, divide by 192. So that will get you your sort of grade trajectory at this point, and then sometime in October, when interim grades are due, this is basically how I'm going to calculate it, including, sort of up to the deadline, that total number of points. So this will change as you do more quizzes and exams as the semester goes on. Any questions on the grading scheme? Okay, so we'll get back into looking at these IR spectra of the different functional groups. And that's primarily what we're going to do today, is just point out the signatures of each functional group. And again, you have a quiz and an exam that opened today, and they're both due tomorrow at noon. The other thing, again, please hit submit when you are finished with your quizzes and exams so that it's recorded. As a backup, you might even want to just take a screenshot of your answers so you have that. Because if you say to me, well, I took it, but my score is 0, I have no proof of that. But if you have a screenshot with sort of the time, then maybe I can work with you. But if there's no submission, ZipGrade logs the time that you submit it. If you just say I did it, but there's no proof, then I can't really do anything for you. So we started on this spectrum, and we said it was the carboxylic acid. And so the R group was the rest of the molecule. And so the CO2H is the signature that we're looking for in the spectrum. And this really broad area here was due to the OH of the acid, and this sharp, intense signal was due to the carbonyl. And sort of, again, to point out, as we'll see, every molecule really has the CH stretching. Specifically, that's sp3 hybridized carbon H stretching. When we see alkenes and alkynes, they're a little bit different. So they have their own signatures as well. We said for this one, there was a nice sharp signal in region 2. Region 2, which was our triple bond. And, based on the choices, that's going to be the nitrile. So keep in mind that, the exam is multiple choice, A, B, C, or D. It's not free form. And, what I've limited the responses to here, there's not alkyne or nitrile, so it's not ambiguous in that regard. But you do see that strong, intense signal there. That belongs to a nitrile stretch. So that one's D. So a student came up after class and said, how could you determine if it's a nitrile or an alkyne? Ultimately you'll be given more data. And so the mass spec of this, again, would have an odd parent mass, and that's indicative of an odd number of nitrogens. So this is a new spectrum. I'll just throw it out there. If you looked at the PowerPoint or that screencast on IR, what do you think this functional group is? It's an alcohol. So the alcohol signature is that diagnostic, very broad, intense signal. So to review what I mean by broad, you see where it starts to drop here. We draw that line from the shoulder, and then it goes back up towards the baseline. So that span of wave numbers is very broad. And so that's the signature for an alcohol. Notice that it goes back up. So it's going back up before it reaches that CH stuff. And it looks different from a carboxylic acid because that OH is more shifted into the CH region. You have separation. And the other thing in region 3, you'll notice there's no carbonyl signature. So that's, 17, 18, 17, 1600. That's your carbonyl. My voice is shitting out today, sorry. That's the carbonyl region. You do not see a signal there, so that cannot be a carboxylic acid. So the diagnostic signature on this one is going to be this signal right here. See how that, any geology people in the crowd, is this a stalactite? stalagmite, what's the difference? But that is diagnostic because it's separated from this. So this region here, again, that's the CH stuff. So CsP3H stretching, which nearly every molecule will have. This little spike here is separated from that, and it's going to be an sp2 hybridized carbon H stretching. So the answer here for this one's going to be alkene. There's also this other sharp signal here. It falls into the region 3, which is the double bond stretching. But notice it does not have the intensity of a carbonyl stretch. So this is C double bond stretch. A carbonyl stretch is typically more intense and a little bit broader. So what I mean by that, it's going to come down sort of a little bit further and have more area to it. And again, it's sort of a visual thing that you're looking for. So to recap, SDBS or NIST webbook. Those are where I'm pulling the spectra from. This is from the SDBS. The ones from the NIST webbook will look a little bit different. And so now if you're scanning from left to right, in the region 1, which was, so region 1, that's XH stretching, so CN or OH single bond stretching. Again, we have the CsP3H here, and then this really intense sharp signal there. That's now due to sp hybridized carbon H stretching. So we find that in an alkyne. And associated with that in region 2 is this sharp sort of medium intensity signal. And that's the triple bond carbon stretch. So overall, this has to be a terminal alkyne. If the alkyne was internal, you would have carbon, triple bond to carbon. Now that ends up being sort of symmetric in a way. And so what it's going to do is it'll decrease the intensity of this stretch where it moves more up towards the baseline and you don't really see it. And also you won't have this present, this really strong stretch. So to figure out if there is an internal alkyne, you basically have to say, does the molecular formula have 2 degrees of unsaturation? And then to further confirm it, we would use NMR spectroscopy. So what is one diagnostic peak that you see in this IR? So there's a carbonyl. If we scan, so this was 1500 about here, 16, 17, 18. So maybe we'll say that's like, you know, about 1700 reciprocal centimeters. So that's a carbonyl. If you look at the responses, all of those have carbonyls, but now there's something that will differentiate them. And the connector to that carbonyl is right here specifically, that little stretch that occurs after, when you're reading left to right, it occurs after the CSP3 stretching. So this little blip right there, that is the sp2 hybridized H stretch of an aldehyde. So now there's this issue, right? How do you know if it's an alkene? Because those occur sort of to the left. That alkene stretch, sp2 hybridized carbon H stretch, occurred over here. But this one occurs after it. So that coupled with the carbonyl is indicative of an aldehyde. Yep.
What peak would appear for amides?
We'll get to the amides a little bit later on. But with the amide, that type of carbonyl it's shifted more. So you're going to look at the where the peak would be labeled in terms of the percent transmittance, the bottommost part. It's going to fall in a different region within, you know, that's 18 to 1600. So that's how you would know it's an amide carbonyl versus the other carbonyls that have oxygen or a ketone and a aldehyde. So here we have, this was aldehyde. So the ketone will not have that little extra CSP2H stretch. What is this? So again, none of these things look perfect like, you know, like your textbook might draw them. So there was a question last class sort of about that. Should I interpret that or not? That's most likely water. So when you run these, you're making a sample, you put it on the detector, and if the atmosphere and the air is not purged out of that, the laser will detect moisture in the air. So there is some subtlety to interpreting these things and not over-interpreting them. Have you guys run IR yet in your lab? Some have, some have not. So it's the instrument is called ATR, which is attenuated total reflection. It's just like a little plate. You put your sample on, you lower this thing, but you're doing it out in the atmosphere. I mean, and there's humidity, and it's detecting that. Yep. So I believe these are the same responses as the last question: aldehyde, amide, amide, ketone. So the last one was aldehyde. We can see that there's this carbonyl stretch here. We have 16, 17, 1800. And if you draw a line down, you see that that signal is greater than 1700. And so that's how we're going to differentiate choices B, C, and D. The answer will be a ketone. Hey, look, there's a friend. We'll let him live. I'm all about good chi. So amide carbonyls will always occur below 1700. That's their signature in the IR. So once you identify there's a carbonyl, see about where it lies, and that's going to help you sort of narrow down your possible choices. And we'll see that again when those slides come up with the amides. Again, how do you differentiate between aldehyde and ketone? Notice that this IR does not have that extra little sp2 hybridized carbon H stretch. What do you notice about region 3, the double bond stretch here? So we would say that that carbonyl region looks sort of like a doublet. And based on what you know about functional group, what makes up a functional group, which one of those do you think would give rise to a signal that looks like that? An anhydride? So an anhydride has 2 carbonyls. And the reason that you see 2 signals there is they sort of each act independent. They can both stretch in the same direction at once. That would be symmetric. Or if they're stretching in different sort of directions at the same time, that's asymmetric stretching. And so that's a different signal. So the anhydride will always look like that. And so that's one way that you can differentiate all the carbonyl containing functional groups. So on the next one, again, anything below 1500 we ignore. If we count 16, 17, 18. So region 3, again, we're looking between 18 to 1600. This carbonyl here, if you draw a line down, that one is essentially right at 1800. So when it's sort of exactly at 1800, that's diagnostic for an acid chloride. So we've seen over the past couple slides, even though there is a carbonyl stretch, between that region 3, where it lies, and maybe some other associated factors, you can differentiate them. So of all of these choices, what I'm going to do first is just draw out sort of what they look like, what we would expect to see for each one, and then do we see something in the spectrum, or if not, can we eliminate it? So that's a primary amide. This is a primary amine. This is a secondary amide. And this is a secondary amine. So in region 1, we see sort of this stretching here. Now that actually is something that needs to be interpreted. And then in region, so we'll say region 1, region 3, so I'm going to do the best I can here. See between 17 and 1600. If I draw a line down from there, I see that that signal is going to fall below 1700. So that's indicative of a carbonyl for an amide. So we can eliminate the amines, but now we're left with, is it primary or secondary? Is there something in region 1 that you think could help differentiate between primary and secondary? It has like a little doublet looking thing. So see how this comes down, it goes up, and then comes back down again? So this would be a primary amide. And the reason that it has that little doublet is that the carbonyl group really only in amides have a significant resonance contributor, where this lone pair will be delocalized onto oxygen. And so you have that resonance contributor, which makes these two oxygens, or these two hydrogens, they're sort of different now because you have more of a double bond character between nitrogen and carbon. So this H is closer to that oxygen than this H. Notice the double bond carbonyl here, but in this resonance contributor, it's more like a single bond. And that's why you see the shift of the carbonyl and amides move below 1700. That carbonyl CO double bond is actually a little bit weaker. So it moves it outside of your sort of baseline of 1700. So weaker carbonyl and amide is below 1700. Any questions? Say it again. That carbon? So the hybridization of the N, the C, and the O are all sp2 in an amide because of that resonance. Even though the nitrogen looks like it's sp3, because you're just showing single bonds, the resonance hybrid that's more prominent is the one where you put the charge, the negative charge on oxygen, the plus charge on nitrogen. Why I did highlight it? Again, the CSP3 hybridized carbon H stretch, like it's always there. So it doesn't really, it's not really diagnostic for us. Again, this right here was your NH2 stretching. So for this one, you won't have that doublet. It'll just sort of go down and up. But again, when it does that, it will not look like an alcohol. Because an alcohol goes down lower, it comes back up, it's more broad. The carboxylic acid is pretty broad. And see this separation here? How they don't merge together? Those are the subtle things you're looking for to differentiate these carbonyl ones. So what do you see in this one? Not a whole lot, right? So again, keep in mind, you know, what the IR is looking for. It's looking for a dipole moment of that functional group that it can excite or perturb so that you see a signal. And sort of this is the basic IR of an alkane. There's nothing really special about this. This is your CSP3 H stretching. This might be some CC stretching or some other CH wagging or rocking or that sort of thing. We said, the alkenes should have that sp2 carbon H stretch. The alkyne should have an sp H stretch. You don't see any of that. So therefore, it's just got to be an alkane. So there's your normal sort of everyday stuff. You can kind of ignore it. So if I asked you, like, what is the color of the doorknob going into your bathroom? I mean, do you actually know that? I mean, you use it every day, but do you pay attention to those details? Like, it's there, but... So what else is diagnostic? We have a carbonyl stretch. So if we look at where that lies, it's between 17 and 1800. So we can eliminate amide. It's only a single peak, it's not doubled, so we can eliminate anhydride. So we're left with aldehyde and ester. So does this look like it has the other aldehyde signature in it? So no, we don't really see that second sort of thing coming down over here. That was that stretch of the aldehyde. So this has to be an ester. So esters and ketones are kind of tricky. But in the molecular formula, what's the difference between them? The number of oxygens. So must have 2 oxygens. A ketone will only have 1 oxygen. But again, if you use some logic, you don't see that ketone was a choice here, so eventually you should funnel into the right answer. So region 3, we can say that's a carbonyl. So there's 1600, 1700. We see that it lies below 1700, so we can eliminate ketone. The rest of the choices are amides. So what type of amide is it? So it'll be tertiary, because if you're looking at, there's your CSP3H. In this region here, you don't see anything prominent that would belong to an NH. So there's nothing there. And the tertiary amide is the only one that does not have an NH stretch. So this one is interesting again. You're looking at what's there, but also what's not there. So terminal alkyne, aromatic ring, ketone, carboxylic acid. Can you eliminate some of them sort of immediately? So probably carboxylic acid, like right off the bat. You don't really see anything coming down this way that belongs to an OH. There's really no carbonyl either. So then that can eliminate ketone. And so that gives you terminal alkyne or aromatic ring. The terminal alkyne, that signal there should be pretty prevalent over here. But we don't see that. So therefore, it has to be an aromatic ring. So something with a benzene in it. And you notice how like this looks sort of a lot different. Again, it's in a ring. The ring is made of sp2 hybridized carbons. There's a lot less degrees of freedom. The bonds can't rotate as much. So when you limit that, you're also limiting sort of the number of stretches that can appear. So we talked at the beginning of the semester about that molecule AZT. And this asks you, what does this signal here belong to in AZT? So region 2. That was your triple bond region. Anyone remember what the structure looks like? Or you can look it up. It's the azide. So it's N3 stretching. See if I can draw it from memory here. I think that's it. So the azide also has a triple bond, but it's present between two nitrogens. So that's why you would see it in region 2. So those were the last, or that was the last slide on IR. I have 2 slides to answer any questions you might have on mass spec and IR before you start taking your exam at 12. Yeah.
What do the beads look like?
I guess I thought I had some slides in here on that. So that would be a primary amine. I think it's going to sort of look like the primary amide, but just without the carbonyl. So in that region 1, you'll sort of have something that looks like that doublet. So this would be a secondary amine. That would sort of look like almost like an alcohol, but it's not as intense. It doesn't go as far down to, 0% transmittance. So not as intense as an alcohol. And again, the reason for that is the nitrogen's less electronegative than oxygen, so it doesn't hydrogen bond as strong. So therefore, that signal is not going to be as intense. And then with the tertiary amine in region 1, you wouldn't see anything. But then you should ask the question, how do I know it's even an amine? And you're going to have to look back to the mass spec data if you're given that to determine if there's an odd mass for the parent ion. But again, since the exams are not short answer or free form, you have to use your intuition and logic to sort of funnel down into that. Yes. Between primary and secondary amide? So again, how do you know it's an amide in the first place? The carbonyl will be below 1700. And then primary versus secondary, you look to region 1. Since that has 2 hydrogens, you should see that sort of doublet looking structure to the NH stretching. A secondary amide only has 1 H, so that will sort of now look like that. But again, those things will not look like OH stretching. So OH versus NH looks very different visually. I'm not giving away any misinformation here or anything, but I mean, what you can do, if you come to a problem you're not sure about, you can go to SDBS and look up sort of what those answers should look like. So you can inform yourself, okay, does the given IR look more like A or B? It's not really cheating, because you have to learn it and make the connection anyway. So the exam is 30 questions. The first 14 are just your standard multiple choice. 15 through 30, you're going to have to scroll to the end of the exam where you're going to see spectra. You'll see IR spectra, you'll see mass spec data, and you have to use that to determine your response. And then as a bonus from 31 to 35, there's a separate set of data that you're going to use those numeric responses. So each of those will be worth 2 points apiece. So you can get a 10-point bonus. Your response should be just a whole number digit. 1, 2, 3, or 4 digits. You're going to look at the data and just put a numeric response. I would say the first couple of those questions are straightforward, but getting the last one right is going to require some thought where you have to put all that data together. Any further questions before we, yeah? So the question was, how do you know which signals to pay attention to? Again, read from left to right, region 1, 2, and 3. Look for anything that's really sharp broad or intense, and that's what you want to clue into first. Then go read the responses and see if you can make a connection. So again, don't forget to hit submit on your quizzes and exams, please.